Welcome to our first video on simple linear regression. In this video, we will discuss the two main objectives of simple linear regression, and also we're going to run an example that will help us start understanding how should we interpret the coefficients of a simple linear regression model. Simple linear regression, or regression models in general, have two main objectives. The first one is going to be to establish if there's a relationship between two variables. We're going to be talking about a positive relationship between two variables if they tend to move together, in the sense that when one increases, the other one increases as well. And conversely, in a negative relationship, we find that if one variable's values increase, the other variable's values tend to decrease. More specifically, we're going to be talking about statistically significant relationships between the two variables, but we will get back to this later. Let's talk about some examples. On average, we expect that people or families that earn higher income will generally spend more of a given product. In this case, we're talking about a positive relationship between income and spending. We could also analyze and test if there's a relationship between wage and gender. We could ask if men are more likely to earn higher wages than women, case in which we're talking about gender discrimination, which is negative and we don't want it. But we can actually use the regression models to test if that relationship exists. Another example that I hope you find odd is relationship between a student's height and that same student's exam scores. We should expect no relationship to exist, and we can use our regression models to test that. Our second objective is going to be to forecast new observations. And what we mean here is, can we use what we know about an existing relationship to forecast unobserved values? Let me give you a couple of examples. For instance, if we know that our sales tend to grow over time, and we actually even know how strong this relationship is, and we know how fast our sales grow, we could use this information to predict or to forecast what will our sales be over the next quarter. Also, if we have data on stores and we know how profitable different stores are, and we know what is the relationship between how much competition a store is facing in a given location, or what the population of a location is and how those variables impact the store's profitability, we could use what we know about previous stores to evaluate the profitability of a new inexistent store. Of course, we don't know how profitable the new store is going to be, but if we know how much competition it's going to face and we know how much people live nearby the store, then we can use this information to forecast that store's profitability. In general, we're going to be talking about two different roles that variables play in regression models. The first one is going to be the dependent variable. This is the variable whose values we want to explain or forecast. And we call it the dependent variable because its values depend on something else, and we will be denoting it as y. The other role is that of the independent variable, and this is the variable that explains the other one, and we say that its values are independent, hence its name. We will denote this value as x, or this variable as x. When we use simple linear regression models, we call them linear because the magic is that we're using a linear equation. And from your high school years, you might remember one of these, where y is a function of x, and there's a term that is added to the function and another one that multiplies the x. In the stats world, we like Greek letters, and we're going to be using a slightly different notation. Our linear equation is going to have a beta 0 term, which we're going to be calling the intercept or the constant, and the beta 1, which is the term that multiplies the x, and we're going to be calling the coefficient of x or the slope of x. And as a recap, we call these linear equations because they will appear as a straight line if we plot them in a b-dimensional plot. Let me show you an example of a linear equation. And remember, our model is y equals beta sub 0 plus beta 1 times x. And let's simply give numbers to those betas. And let's say that we have a linear equation y equals 4 plus 2x. Let's analyze what the 4 means. 4 is the distance from the horizontal axis at which the line crosses the vertical axis. In this case, if x had a value of 0, y equals 4. And we see here that the line is crossing the vertical axis 4 units above the horizontal axis. The slope in this case is a 2. And it means that for every unit increase of x, y will increase twice as much, or 2 times as much. We see here that x increased from 2 to 4, while y increased from 8 to 12, twice as much. Let's further understand this and wonder what happens if we change the intercept. In particular, let's use a larger intercept. Let's change the intercept to a 9. We see that we're moving the line upwards, meaning that we're increasing the distance from the horizontal axis to the point where the line intersects the vertical axis. We could also have a negative intercept, which would imply that the line is intersecting the vertical axis below the horizontal axis at a negative number. If x were 0 here, y is minus 2. Now what happens if we change the slope? If we change the slope, we're changing the sensitivity of y on values of x, meaning how fast or how slow y will change when a unit of x is changed. If the slope were a 5, that means for every unit of x, y is going to increase 5 times. So you see that we have a much steeper slope because y is growing much faster than it was before when we had a 2. What would happen if we had a 0 slope? This would mean that it doesn't matter what value x has, y will always be 4. And if we go all the way around to a negative slope, a minus 3 in this case, we have a downward slope, and this represents that y will decrease 3 units for every unit of x. Now in this case we're talking about very crisp and clear straight lines, but data in the real world does not behave like this. Data in general is going to be a series of x and y observations that on average may follow a linear pattern, and that's why we use linear regression models to represent them. But the line is not always, and actually most generally, not intersecting or passing across any of these dots. Rather, there are going to be errors that we can measure, which are the distance between the dots in the real life and the actual linear regression. And what linear regression is going to do is trying to draw a line that minimizes these errors. But the important aspect we're going to take away now from this is that our linear regression model must include this error into it. So this is how our linear regression model looks like. It is y equals beta 0 plus beta 1 times x plus the error term. So let's recap. Y is the dependent variable, the variable whose value depends on all other parameters in the equation. X is the independent variable that helps explain the variance in the y. Beta 0 is our constant term or intercept. Meanwhile, beta 1 is the slope coefficient for the x. And epsilon, which is a Greek term to symbolize something that is very, very small, is going to be our error term, which we're trying to minimize. Now let's look at an example with actual data. We will try to explain a family's consumption of a given product. So think for the moment of any product. It could be cereal, it could be toys, it could be books. And try to wonder what determines a family's consumption of this product. And you may want to pause this video now and spend a couple of minutes thinking about what could you use to explain a family's consumption of a given product. Alright, maybe you thought about attributes such as how large the family is, and in general, larger families would necessarily have to consume more. But if you recall our early example, we talked about a positive relationship between income and consumption. And this is what we're going to have in the data we're going to use. Our data is going to be a series of 40 observations of 40 different families and their weekly income and consumption of a given product. So we have 3 columns in our data. The first one is going to be an observation ID, which generally has no meaning whatsoever. And the other 2 columns are going to be income and consumption. So how could we use these 2 columns in a simple linear regression model? Remember, our model has a dependent variable and our independent variable. And in this case, we're trying to explain consumption based on income data. So consumption is going to be our dependent variable and income is going to be our independent variable. And of course, the assumption we're making and what we want to test is if income is good enough variable to explain consumption. If we throw this into a statistical package, such as Gretel, this is what we observe. And for now, don't worry about all the numbers you see here. We will learn about them later. Focus on the coefficients, which are 2. And Gretel is indicating that our constant term is 49.1334 and that the coefficient for income is 0.852736. If we wrote this into our equation, we would find that consumption equal to 49.13 plus 0.85 times income plus the error term, which is going to be very important. Now, what do these numbers mean for our model which tried to see how did income explain consumption? Remember, our model is this one right here. Now let's start with 49.13. If income were 0, consumption would take this value, and consumption would be 49.13. So using this, we could interpret the intercept as the consumption level of a family with 0 income. Now this makes little sense unless we assume that there's a state-run program that offers financial aid to families with no income, such that thanks to this aid they can have some consumption, but more generally the intercept will not have an intuitive interpretation, meaning that in most cases we will actually be ignoring it. Now let's talk about the 0.85. This means that for every unit increase in income, consumption will grow by 0.85. We can call this the marginal effect, meaning that on the margin, income will grow 0.85 for every unit increase in income. And let's put some dollar numbers to this. Let's say a family's income is 100 more. So 100 times 0.85 means that for every $100 of income a family earns more per week in this case, the consumption will grow on average an expected of $85. Worth noting, the slope will always have an intuitive interpretation, which is the sensitivity of the dependent variable on changes in the values of the independent variable. And we will finish our example by showing the initial observations and the fitted linear model in the same plot. Here in this plot, the horizontal axis is income and the vertical axis is consumption. The 40 red dots you see represent each of the 40 observations of the families for which we had data on income and consumption. You can notice that they follow a growing trend, but they are not at all in a straight line. What we did, however, was draw a straight line that closest resembled the pattern followed by the dots. And this is the blue line which shows the fitted values from our linear regression. What our estimation procedure did was try to draw a line that minimized the error between the red dots and the blue dots, but we will talk more about that later. This is all for this video. Thank you.